All right, how's everyone doing at Recon? Day 2, let's hear it. Come on, let's go. Woo! Yeah, that video gets you fired up in the morning. It's 10 a.m. I've had a liter and a half of coffee, so I think we're ready to go. I'll let everyone find their seat. Cool. So, hi everyone. I'm Luke McLaren, otherwise known as Data Local TMP, and I'm here today to talk to you about WhatsApp hacking. And this talk is called Call Crash Repeat because it's all about bugs in WhatsApp at the calling layer as well as the messaging layer. But just before we get started, I want to say thanks to the organizers of Recon and Hugo. It's always fantastic to get to come here, spend some time with my in-laws in Montreal, and present to security researchers. So without further ado, I'll get underway. So who am I? I'm Luke. I generally share security research at Data Local TMP. For the Android security researchers, you'll know that as the Scratch directory. I'm also a guy who hasn't started the timer, so just to make sure you guys are on time. But I'm generally spending a lot of my time digging into WhatsApp messaging and VoIP stack. I do a lot of hacking on the Meta platform. So just to have like hands, who uses like WhatsApp every day, would they say? Okay. And then who uses Messenger every day? Okay. Decent. So my last talk in Argentina at Echo Party was all about messenger bugs. So it's kind of funny. I do the messenger talk where WhatsApp is most used. And then I would say I do the WhatsApp talk in Montreal where messenger is probably more used. A bit strange like that. Anyways, I recently started working for a French security company called Epsilon. If you're interested in security research, we're a small group and you're looking for a job, feel free to reach out afterwards. Really great group of guys. It's about 10 or 15 of us. So cool. Today's agenda, pretty simple, but we're going to go through WhatsApp as a platform and sort of like the why, what, where's, how's, all of this. So like calling architecture as well as end-to-end encrypted messaging, how that's done. Then we're going to go through 4 bugs, getting sort of like progressively more complex. So the first bug, I think everyone in this room is going to be able to recognize the issue, but then at that very last bug, you're going to see that it's going to take a lot of like RE to get there. At the end, I'll take questions. If anyone's got any burning questions, I'll also be out back afterwards. So cool. So to get started, let's talk about the WhatsApp platform as a whole. So WhatsApp really doesn't need much of an introduction. It's around 2 billion users across what I would consider every country in the world. It's an app for personal, business, or group communications. And the big thing with it is that it does end-to-end encrypted messaging, right? When you think of an end-to-end encrypted messaging app, a lot of us probably think Signal, maybe Telegram, but for people who are outside of security, I bet you they think of WhatsApp first. Someone in this room is probably thinking, hey, Luke, not everything is end-to-end encrypted. You are correct. Some of the messaging is required like metadata for routing calls or routing messages. So WhatsApp will see who you're calling or who you're messaging, but never the contents of the call or message. And there are so many features here in WhatsApp. You might not use all of them, but they are still there for using. So we have things like voice and video calling, event scheduling, voice chats, which we'll see more of later. We have screen sharing, all of these things, right? And really what this represents is attack surface for security researchers like you to go out and look at, right? There's so much here. There's more than enough for all of us to chew on. But the big question with WhatsApp, and something I wanted to address real quick, is why? Like, why should we spend some time doing security research on WhatsApp? And, for me, for you, for everyone, it can be different. This is 2 billion users using this app every day. The first one is obviously beaucoup bucks, right? That's the extent of my French in this presentation. I'm sorry, everyone, but beaucoup bucks. At WhatsApp Pwn to Own this last year in Ireland, if you rocked up with a one-click RCE, you're making $200,000 USD. If you rock up with a 0-click RCE, you make 300,000 USD. Does anyone know how many people submitted bugs to Ponto and WhatsApp? Just curious. Yeah, big donut. Big donut. And why is that? Because for an Android or iOS RCE for WhatsApp, you're looking closer to like $8 million USD. So very expensive. Here's my sort of counter to this argument that like, why would Meta ever go to Ponto own? Well, Meta versus the market. Meta doesn't mind if you rock up with a 1-click RCE that's like hardly reliable. You need like 4 attempts and there we go. Like you can rock up with a janky bug and get paid out. Whereas if you go to the market, you're going to need something that is stable and something that's long lasting. Like you're not going to get $8 million off the bat with a janky bug, okay? The other why you might have is you might want to protect users from 0 days, okay? And we have Daniel and Bill actually talking tomorrow from Citizen Lab Toronto, and they just did a lot of work with Meta on preventing a WhatsApp exploitation campaign. So that's really fantastic for them. And if you're looking more into this sort of stuff, I really recommend Maddie Stone's talk on when binaries aren't when exploits aren't binary. For me, it's because I get to present at Recon 2025 to all you lovely people. And, you know, WhatsApp is a hard target, and I like sharing my research with you all. So for where WhatsApp is, I just want to point out that WhatsApp's available on many different platforms. And in this presentation today, you'll see that the bugs sort of span those platforms. So at the lowest level, we have web. Web is like, it's the lowest tier client. You can only really do messaging. You need to have a paired mobile device, and it requires that your device be on. Whereas for the desktop clients like Mac OS and Windows, these are fully fledged clients, okay? They're essentially equivalent to the mobile clients, which are the flagships, but you don't have the ability to register for WhatsApp using them. And then finally, you have iOS and Android. These are the flagship clients. These are written in Objective-C and Java, and then like for their respective platforms, right? And then we have a shared C and C++ code base. So if you're looking to research RCE for WhatsApp, it's these 2 native libraries where you're going to see that like native components, okay? And really those represent the most interesting components of WhatsApp for remote code execution research. So there's our web client. There's our Mac OS, Android, and iOS. And some of you might be thinking, wait, does Luke use his personal WhatsApp for research? Yes, I do. And don't add me on WhatsApp. You'll get some weird messages. So, all right. So cross-compilation. So how is WhatsApp built? Okay, we're getting through it. The C++ code base is one core code base that is then compiled for multiple different platforms. So I was saying before to some people in the hallway, if you look at the CVEs on the security advisories for WhatsApp, you'll see that all those bugs generally span like iOS, macOS, Android. It's the same code base, just compiled for different platforms. And what's nice for us as security researchers is that native bugs in one platform will rear their head in others, and we'll see that later on. Unfortunately for us, the binaries are stripped of symbols, but there's extensive logging in the native binaries, and if you're doing research, you can find those logs, not in a standard location, but in these platform-specific locations. For iOS or Android, you will need a rooted or a jailbroken device. For Mac OS, you can just sudo and read that, or like just read those logs there. And something we'll see in a moment is that as these code bases are compiled for different platforms, structures are going to change between those platforms, and we'll see offsets are different as well. So this is just to hammer that point home of a shared code base I don't need you to understand the code that you see here. I just need you to recognize the general structure of it. So we see a log statement up at the top. We see some logic there, and then we see another log statement at the bottom. Okay, this is Ghidra output for some portion of lib WhatsApp on Android. Actually, this is WA call signaling. This is the call signaling portion. If we look at the Mac OS build, I want you to recognize that's the same structure, right? We have a log statement, some logic there, and another log statement, and then the same for iOS. So this is one shared code base compiled for 3 different platforms. So if you have a native vulnerability in one part, it's going to show up in the others. Now, let's talk about the calling architecture of WhatsApp. There have been very substantial bugs found in the calling architecture of WhatsApp, and we'll talk about that in a moment. But for call establishment and maintenance, so if I'm setting up a call with you, they use XMPP signaling. This is all closed source. This is WhatsApp code written for WhatsApp, right? It's written by WhatsApp for WhatsApp. And spoiler alert, if you want to read all about it, you can just search this particular string in the binary and you'll find all the functions, right? Like you can see it up at the top there. This is responsible for setting up calls, tearing them down, screen sharing, muting yourself, video, really everything when it comes to maintaining and establishing calls. When it comes to sending actual data across the network, so like RTP and RTPC streams, or RTCP streams, you have PJSIP. So PJSIP is a location for very significant bugs, but it is open source / WhatsApp has made a lot of heavy modifications to it to make it more secure. So if you hear about a PJSIP bug, but it's not associated with WhatsApp, it's likely that they already mitigated that through implementing some sort of like control flow integrity or something like this. It's going to manage the construction and encryption of like RTP packets. And you may have heard that in 2019, 1,400 phones were, or at least 1,400 that we know of, were exploited using this particular CVE in WhatsApp. So it's a very significant place for research. And finally, one that we won't talk too much about today, but you'll see a little bit of it later on, is WebRTC. So WebRTC is responsible for taking your voice, encoding it into data, and then giving it to the RTP packet to stream over a channel that XMPP is set up, okay? And what you'll see is that we have a whole bunch of video and audio codecs that are packaged within WebRTC. One that I want to point out, and you'll see later, is MLO. This is Meta's proprietary or open source audio codec that they created. It's Meta's low bandwidth audio codec, and we'll see that show up later on. It also does some other stuff with bandwidth estimation, but we'll skip through that. And here's just a short video. I like to package a lot of videos into my talk. So this is just showing you when we establish a call. This is just a little tooling I've set up here. When I establish a call here, you'll see an XMPP stanza pop up, an offer stanza. An offer stanza represents offering up a call to the world or to a group, right? When someone joins, you'll see a couple of other stanzas. You have a video stanza that represents, hey, I'm streaming your video, you're streaming video to me, as well as a transport stanza that will do the construction of like relay servers. There we go. And what you'll see is as we mute and unmute or like turn on and off our video, there's corresponding stanzas that are sent out. So we have some mute stanzas and video stanzas. If we share a screen, we have a screen sharing stanza. And if we stop, similarly, right? If we terminate our call, we get a terminate stanza. And if we rejoin instead of an offer, this time we do an accept call because that call's already established, as well as an encryption rekey stanza because we need to reestablish our encryption keys at this point. So hopefully that's very clear to everyone. When you set up a call, there's a bunch of XMPP messages that are sent to like say, hey, I'm joining, here's our transport, here's my video, all this sort of data. And each one of those lines is actually quite a larger document. I've just shrunk it down so that we can see it very easily. Okay. I like to do a little bit of foreshadowing in my talks. So like I just said, that offer stanza is actually quite a bit larger than just that one XMPP line, right? It can have attributes within it. And one attribute that we'll see come up in a later bug is called the silence attribute. This has to do with when you call someone and you don't want them to get like a loud notification on their device. Say you have a group of 200 people and you go, hey, anytime someone calls, that makes a lot of noise on everyone's phone. Let's set the group to be silent, so any calls are just quiet. And this is a list of reasons. You can't really read that, but it does say like group settings, scheduled, lightweight. The one that I want to point out today is something called VC init, VC wave, and VC wave all. You can't see it, but you will see that voice chat VC. This is a new feature WhatsApp has added within the last year or so, and we'll see a bug in it in a bit. And for some heavy foreshadowing now, if you look in Ghidra at some of the functions within lib WhatsApp, you'll see symbols stripped off of like the entire function. But if you go to the PJSIP project on GitHub, you will be able to often map these stripped functions to actual PJSIP functions. And I'll put these slides up after the talk so that you can read directly and understand this. Finally, end-to-end encrypted messaging. All messages on WhatsApp are end-to-end encrypted. We're not going to talk about the actual underlying cryptographic algorithms or key sharing mechanisms. You can look at the white paper. But what I do want to point out is if this is a space for you to do research later on Android, if you want to make modifications to the encrypted protobuf before it's encrypted, you can hook this function here and modify the input stream of characters, which represent the protobuf before it's encrypted, and anything that comes out will be sent and processed by the recipient client. All right, cool. We got through WhatsApp. Now let's get to some bugs. Here we go. So the first bug we're going to talk about is event URLs and how they were perhaps not validated correctly. So this is a new feature within WhatsApp. It's called events. And what it allows you to do is in a group, you can schedule an event. Your friends can all RSVP. One thing I want to point out is there's this little video icon, right? Instead of a real event, we can do a virtual event and we'll all join on the camera, right? Let's stay inside, not touch grass. Let's just let's just get on the phone. So, so this is a new feature in WhatsApp, and it lets you set up a call for you to meet your friends. Everyone can RSVP, and interestingly, we can associate a video call or a voice call with this. About 10 minutes before the call is scheduled to start, WhatsApp in the background will actually start that call up for you without any user interaction. And then the button which says respond will turn into a join call button. And if you click that, it'll navigate you to a deep link URL. I don't know, does anyone know what a deep link URL is? Okay, so a deep link URL is like if you go onto a browser and you see like contact us on WhatsApp and you click that and it opens up in WhatsApp, that's a deep link URL because it's reaching functionality deep within that app. So this is similar type of link here. And if you're doing research, allow guests in this create event portion. I haven't researched it. I think it would be interesting for research, so feel free to take some time. Here's the event going from respond to join call. And I'll play this video here. And I'll skip through a bit. We're just creating an event. And what you'll see is that, or I'll explain to you because it might be hard to read, is that we dump the protobuf here associated with the event. And you can see that the deep link URL there is being encrypted and then sent to the recipient's device. And if they were to click that join URL button, or join call, it is join URL in a sense, they will join the call and your event begins. Okay, let's see. All right, can you guess the bug? Pretty simple, right? There's no validation on that URL. So if I skip through a little bit and create another event, so here we are. If I skip through a bit, create another event, and then replace it with my personal website on iOS, if you click that, it's going to just redirect you to any site I want. There's no validation there, and there's no indication to the recipient they're about to browse outside of WhatsApp. This can be really powerful for something like a phishing campaign, or if you're going to do deeper exploitation. Of course, the bug, iOS, it's not validating call URLs before navigating, and it has this type of impact. Very simple bug, right? I think we can all recognize that. The fix for WhatsApp was to just implement link validation. Very simple stuff. Now let's talk about a more intricate bug. This is a bug in PJSIP, or at least how WhatsApp implements PJSIP in the calling architecture for groups. And this has to do with how you can start a WhatsApp call. So, of course, people at the back are going to have a hard time reading all of this. I'll point it out here. But this is the offer stanza. So this is what is sent out across the network when you create a call. So if I call a group, I'm setting an offer stanza. And within an offer stanza contains a whole lot of metadata about the call I'm trying to create. So those stanzas, they're sub-elements within the offer element. You have audio and video, which says like, hey, this is the type of codec I'm going to use for video. This is what I accept. This is how big my screen is. This is the resolution or like quality of my audio. But you also have this element, and this is the more interesting element. It's called group info. So anytime I create a call, I say, hey, this is the group I'm calling, and for each member of that group, each user in that group, we send out a user element. So user this, user that, and then user me. And when it's user me, we include a capability element. And the capability element is going to include my device's abilities for like encoding and decoding, all right? So just to go all the way from the bottom to the top, there's going to be a capability element that describes my device within a user element, within a group info element, within a greater offer element that starts a call. And within that capability element, there will be a set of raw data, okay? And the capability element sort of looks like this. You can see actually later on, if you want, you can see at the bottom, there's raw data being put in there. And my device's capabilities are being encoded as like a byte stream. So when you see raw data in something like this complex, I don't even think you need to necessarily think like, oh, I need to understand this data really well before. No, just go in there and set all Fs, set all zeros, like just put something weird in there and see what happens, okay? And I want to show you what happens when you put weird data in weird spots, all right? If you walk away today with anything, weird data in weird spots, you don't need to read this. I just need you to recognize some components of the general structure here. Okay, so on the far left, we have an attacker device. This is an Android device that will be injecting weird data. In the next to it there, on the left, receiving the call right now, is a victim device. This is someone who's in the group unsuspectedly joining and about to, well, receive weird data. Down here at the bottom, this is the logs streaming from the attacker device, and just above that are the logs streaming from the victim device. In the middle, we have the like POC that's modifying the data. So if I let this run, we'll see we modify our data here. I sort of highlight it in the middle, and you'll see this if you look at the slide deck afterwards. And the moment the device who is a victim joins the call, you're going to notice something here. We get a native crash at the attacking device, but wait a minute. Here we go. We get a native crash on the victim device. So this is a memory corruption bug that we're about to deal with here. And this is that sort of first step to getting RCE on WhatsApp. Or at least that's what I thought when I saw the bug. And I was really fired up. I was like, yeah, baby. But you'll see in a moment, things change pretty quick. So we have the crash dump here on Android. and we can see the faulting address. First of all, this might be recognizable to everyone in here, but this is a really low address. It essentially looks like 0 plus some offset. So we can see, and I've highlighted it here, this is Android. It's in the VoIP signaling thread for WhatsApp. We can see the top highlighted portion in red is the faulting address. X9 actually contains that address, and I highlighted X8, register 8, just because that's the data that's trying to write into that address. This is an out-of-bounds write primitive. And the last thing I highlighted there is the backtrace. This is the instruction we crashed at. So we'll look at that in a second. But what I want to point out is that because this is a native bug on WhatsApp, we also see it crash in iOS, okay? And we see it crash in Mac OS. These are older iOS versions, but you can see that the bug was early September of 2024. So when it comes to reverse engineering this, of course, we start with the last instruction to execute. We can go into our favorite decompiler of choice. I use Ghidra here, and you can see that it's a store instruction, okay? So we're attempting to write out of bounds. And we can actually see the specific location in the pseudo C code that is crashing. This is something associated with like getting time, like we see the clock get time, right? And some like nanosecond being written somewhere. Well, this is that setup and payoff I was talking about before. This is the PJSIP function called PJ get timestamp. And that was identified through doing a little bit of looking at the call trees. All right, we're doing a clock get time. Where else would that maybe be done, right? And we can see what's happening here is we're trying to write the value of the current time into an offset of a null pointer deref. So, the out of bounds write to unmapped memory, right? We're storing x8 into this 0x0, so a null value at some offset. And unfortunately, because we can't control the base pointer, we're never going to be able to write into a location that is actually interesting for exploitation. My hypothesis with this bug is that the malformed capabilities data that we sent across the offer stanza is going to cause an object not to be initialized properly, and then later on it's processed and triggers this bug. And really as good as I got was being able to play this for the meta people.
Come on, you guys. There it is, right there in front of you the whole time. You're dereferencing a null pointer. Open your eyes.
Yeah. Yeah, Bret Hart, you said it, dude. Great. Awesome. So the impact of this bug is really that it's going to crash all the attendees of a call. So if you have like 200 people on a call, you can crash them all out of the call with this, or at least you could before this bug was patched. And the fix here was that Meta went in and fixed the processing of that null object. That doesn't happen anymore. Okay, cool. Some of you who had a keen eye on the schedule, or at least like the talk descriptions, would recognize this as being like the final bug. And you're looking at the time and you're like, oh, we're about half an hour in. I actually include a fourth bug here because it got patched like 2 months ago. So I said, you know what, this bug's so good, it's great for Recon. So this will be another logic bug, and then we have one after this that I think is really interesting. But this one's great too. This is a voice chat bug, and this is all about a logic error in WhatsApp that allowed me to enable someone's video stream without their consent. And you'll see how we were able to do that. Just to give you the background, knowledge required for the bug. Voice chats still are in WhatsApp, and they're a new feature that was introduced around November of 2023, so a little under 2 years old. Voice chats allow you to instantly talk. I have quotes here because this is straight from Meta's website for the feature, but they're essentially like Discord rooms. You know, if we have a group chat of like 250 people and we don't want to set up a group call, you know, it's a little bit loud, let's create a voice chat and people can just jump in or out. It's kind of like Twitter rooms as well. And in a moment, I'll show you that they aren't just available to groups of 33 or 256. That's still the case today if you use parts of this bug. What's going to happen is it'll start quietly. It won't ring the group members. And it's similar to Discord. And the way that you actually reach voice chats, okay, is that offer stanza we just looked at with PJ-SIP, with that PJ-SIP bug. Essentially, it's an offer stanza that is going to contain another element called silence, right? We saw silence. And the silence reason needs to be voice chat init or voice chat wave. And what will happen is an Android device will say, hey, I see this silence reason. This must be a voice chat. So we'll see that bug in a second here. So what I'm doing here is this is just my tooling in the middle. And we're going to start a voice chat. So I'm actually starting a voice call on the attacker side. I generally use attacker on the left, victim on the right. I don't know why. And the attacker is going to send a call. And I just want you to notice quickly that instead of showing up like a normal voice call, we have this voice chat drop down here where we can just join in. First of all, this group is only 5 people big, and it's actually all me with 5 different phone numbers. So really just talking to myself. If anyone wants to talk to me, please, but yeah, I have this group here, 5 people. It's not 33 like WhatsApp generally requires for this feature. And if we join in, you'll see a different interface. This is actually after the bugs patched. So you'll see this interface down below. The interface actually looked different at time of exploitation for this bug. But this is definitely a voice chat. Android thinks this is a voice chat. This did not affect iOS or macOS, just a heads up. This was in the Java parsing logic of Android. All right, so spoofed voice chats. I have a voice chat. I'm going to pretend that I have a voice call. I add this silent stanza, and it makes it look like a voice chat. This is the old interface, and I'll explain why it's been changed since in a moment. But when you add this silence attribute, it's going to convince Android that you're in a voice chat. And if you're taking a shot for every time I say voice chat, it's going to be about a long day for you. And what happens is if you pretend that a video call is a voice chat, when you open this up here, the video streams of the non-voice chat users get injected into these like strange places. There should never be a video stream right there. But it's not enabled on the recipient's device. There's no real impact on the recipient's privacy at this point, right? They join into this voice chat, they can see you, but you can't see them. And you go, okay, well, this is weird, but nothing really, no issue on my part, right? And this is when I thought, okay, this could be really significant if we can turn that on. And the first thing I noted to myself is that the design elements for voice chats, you can see these squares here, look very similar to the design elements for screen sharing on WhatsApp. So if ever someone shares their screen in your WhatsApp group, they will share it into the middle, and then everyone's on the bottom with their video streams. So I go, what happens if people start sharing their screen as we have this weird voice chat, okay? So this is a video here. This video is a little bit longer. I was going to skip through it, but I think it's maybe good to just like realistically show how long it takes sometimes to get set up for bugs. One thing I just want to point out actually right at the beginning too is right as I start this call and I create this offer of a voice or a video call with that like VC init or VC wave, if the victim tries to answer this call, right, it says group voice call, which is funny because it's a video call and it's pretended to be a voice chat. So I don't know why it's skipped there. But if they try and answer it from the dropdown, just note that WhatsApp crashes silently. This is a null pointer deref in Java, actually. So it's not an interesting bug, but this is a very buggy path that we're about to take together. You can see all the other devices are going to be joining in. And so an iOS device just joined in who has his profile photo set to a Tamagotchi in honor of Natalie Silvanovich, who always does great talks here. So shout out Natalie there. And you can see that the iOS device is now sharing its screen. The setup can actually be quite a bit faster for this bug if you were truly going to exploit it. We'll just skip to about the minute 20 mark where everyone's now in the group chat. People are sharing their screens. And now the victim is going to go and answer the WhatsApp call themselves. So here they go. They open up WhatsApp. This is just WhatsApp being annoying. It's not necessary to the bug. And when you go in, you'll see, hey, there's a voice chat going on. Don't you want to join? So join up. And as that drops down, you don't have to mute yourself, but you'll notice that, boom, we have our video stream. The victim has just begun streaming their video to everyone, thinking that's a voice chat. And you'll see me waving here. If you can recognize the hand, maybe. Yeah, so pretty significant bug, okay? This is like really bad from WhatsApp's perspective. You should never be like in a call where you're sort of like non-consensually sharing your video. And watch what happens when you try and join again. This is how buggy this feature is. So let's see, enter. Waving a bit more, doing some things. If I try and hang up, okay, WhatsApp just crashes, and actually a ghostly image of yourself stays in the call. So even if you try and hang up, you're not going to be able to. You can't turn off your video in this state. You'll notice on the bottom there, right, there's no way to disable video, and not really any way to hang up either. Okay, so the bug here was that under certain conditions, it was possible to enable a recipient's video stream without their consent or permission. This bug was high impact with WhatsApp, and I reported it December 7th, so just before Christmas. That helped with the presents, of course, and it was patched December 13th. Something for you security researchers out there who might be doing bug bounty. I just want to point this out. It's worth noting that if you have a high impact bug that like Meta or Google can patch at the server level, and they're beginning to ask you questions about that bug, answer those questions really quick, because if I had waited until past the 13th to use my proof of concept to answer questions, I wouldn't have been able to answer those questions. The impact might be lower, and that might result in a lower payout for me. The fix here from WhatsApp side, the reason why they were able to fix it so quickly is because that offer stanza is unencrypted. WhatsApp's able to see that. So they were able to just say, hey, any offer stanzas that are trying to be routed with this silence attribute, just kibosh them. They can't go through anymore. But what you'll also note, a moment ago, I said that the design elements of voice chats now have changed. They don't even allow you to render a video stream there anymore. Like those design elements are completely different. Okay, cool. So that's where the talk would have ended had this bug survived past, I think, March 31st. This bug here is all about transport stanzas. So this bug is about when we create a call with one another. I will send a transport message to you, and we will agree on a relay server to send our call and like voice and video data through. So transport stanzas, like I said, represent data that are associated with a call. They include information about relay servers as well as the type of connection. And a transport message, interestingly, doesn't need to be its own message all the time, okay? A transport message can be its own message, but it can also be a sub-element to elements like video or relay latency, right? I'm sharing some latency stats with you. Here's a transport element to describe our connection. Same with video. It's sent when you're creating a call, but it's also sent when you like reestablish a video stream or when you reconnect to a call. And we'll see that using my tooling here in the middle. I'll just be dumping out XMPP stanzas. You'll note that instead of an Android device, now I'm attacking a Mac OS client. And when we create a call here and the Mac OS client accepts, you'll see that we have two transport message types being sent. One in the video and one in the transport. Sorry, it's the transport element and then the video element. All right, so these are the transport messages that are required to start a call. How about if we, emulate a short disruption to our network? So okay, all right, my internet's bad. I just reconnected. If you have a short disruption, you send another transport type message of 4. And then if you have a longer disruption, okay, so DLT2 is now reconnecting for a longer period of time, your relay servers may expire and you need to recreate those. So when you connect after a larger disruption, you'll see a bunch of messages of 3 and 9. All right. And I don't know about you guys, but when I see numbers like that and I'm like, okay, 1, 2, 3, 4, 3, 9, I started asking myself, what about these other types of messages? And what happens to the recipient if they receive other types of messages? So we'll skip like 1 and all the others. The one that was interesting, though, was message type 2. So if I run this, you'll see that my script is now replacing the 4 value with the value 2. So the recipient answers the call. This is actually someone else starting the call, which is still me. But when I join, you'll see a transport message type of 2 being sent. All right. And what I want you to note on the Mac OS side is that I join the call for a moment, and then my Android device disconnects. The Mac OS sees that I've disappeared. And me in my laboratory, I go, okay, well, I need to read the logs. So I keep hammering message type 2. All right. I'm reading logs. And then something interesting happens here. We'll just give it a second. And I'm reading logs. Oh, wait a minute. Where'd my Mac OS client go? Uh-oh. That's not good. Well, maybe it's good for me, but this is a memory corruption bug because I've been sending message type 2. Possible pointer authentication failure. Oh, all right. Yeah, we're not going to send that to Apple, actually. We'll hold on to that one for us. So let's have a look at what that bug is. Very interesting and potentially significant too, right? This isn't that 0 plus an offset anymore. This is like a real, like almost mapped address. So we can see current invalid address. Something to note is that this actually was just crashing Android clients, or not crashing them, but like just removing them from the call. This didn't affect Android. And so far, I only ever saw it on iOS. You can see this version that affected was released March 31st of this year. So it's fairly recent. And you can also see that this was the media parsing thread for WhatsApp. This is the error, and that's the offset we crashed at. Attaching LLDB, so using like GDB or LLDB, I attach to the process, and I trigger the bug again. And I can see that the crashing instruction is this load instruction, right? This ARM64 load instruction. And I can see that we're reading offset 17 of x0, so the first parameter to a function, and we're trying to load it into register 9. All right, that's interesting. So this is an out of bounds read. If I look at the registers at this point, I've highlighted in red there, but this is the crashing instruction. And we can see that there's a bunch of strings stored in the registers at this time, something associated with WebRTC MLO decoder. All right, so it looks like we are having troubles in the MLO decoder stuff. All right, well, why don't we attach with LLDB and just run this again and see what normal execution looks like. So the first thing with normal execution that I want to point out is that first object in X0 is the same as the object in X1. Like they have the same structure and components, but they are different objects, just pointing to the same thing. And as we execute this function, we eventually see that it is trying to get the length of the name of the object associated with this like configuration parameter. That's a bit confusing, but just know that this is a parameter being used to start a call. And it eventually gets corrupted. It goes into a mem compare. So that corrupted object eventually leads you to a length that's used for a mem comparison. I initially read it as a mem copy. I guess we see what we want, but it was a mem compare this time. Still potentially exploitable though. And in Ghidra, I just started walking the backtrace, right? So this is that ARM instruction, out of bounds loading. We can see it here. You can see that I've renamed it mem copy. It's actually mem compare. I presented this to a friend as a practice, and he's like, I think you've missed something. But sure enough, it goes all the way up to here, where you can see that it's triggered within a while loop. So there's like a nested while loop here that keeps calling this. And it's actually iterating across all these VoIP parameters. One other thing that I just wanted to show you quickly, this is actually Ghidra here, is that that string, that low, let me grab it here. This string that we see here, web RTC MLOW decoder, low pass cutoff frequency. So like the cutoff frequency that if you go below, it'll get rid of. That is actually found in this function here, which is associated with creating an MLOW decoder. So you can see create MLOW decoder. And as we come down, you can see the string low pass cutoff frequency. This is actually Ghidra, just showing you now. Cool. So the hypothesis is, all right, while we're creating a call, if I use a transport message type of 2, one thread will begin tearing down that call because it's an invalid message type, whereas another call is now trying to establish. And because they're happening so closely together, the media thread is trying to access all these VoIP parameters or configuration objects, and then one of those objects is teared down while it's trying to be stood up, and we end up getting a use after free in WhatsApp's media thread. This had a lot of impact for Mac OS. Okay, we couldn't trigger it on iOS, but it had a lot of potential for RCE. And the fix here, big shrug. It was there one day, gone the next. I chatted with the Meta engineers, and they said, "Yeah, we've actually refactored that portion." I go, big tears, and you know what? That's okay. Bugs disappear. I had a lot of open questions about this bug. If you go grab the IPA or Mac OS client for this, you can try and reverse engineer it yourself. But a lot of questions revolved around whether we could control that pointer or not. So that's where this bug died, except my mother-in-law sends a message to our group one night, and she goes, "Hey, father-in-law is trying to make the switch from a flip phone. We need a smartphone. Does anyone have a smartphone that he could borrow, preferably iPhone? He finds that an easier interface to use." And I go, "I have an old iPhone, and I swear there's no 0 days on it. And please don't tell them that there was a 0 day on it at one point." But after I handed off my old iPhone XR, I looked on the shelf and I go, I still want to look at this bug. What do I have? Well, I have an iPhone 6S, even older, but it has the same version of the WhatsApp client that I was exploiting in Mac OS on iOS. So let's see what happens if I trigger on the exact same version. So there's the iOS device on the right. And wouldn't you know, I set up 2 Android devices to attack. And and there's iOS crashing on this native bug. So that's where I go, oh my God, sorry about this background too. I mean, I like cats, but there we go. So this bug did affect iOS, and there's our crash dump. You can see that we have a separate invalid address being accessed through the kernel. And so this means that we are we have the ability to maybe groom something in there. It's not a fixed address. It can be changed. So this is where the end of this bug is. It's been patched. You can potentially still trigger it in old versions of WhatsApp. If you're interested in that, feel free to come up to me afterwards. And thank you very much for listening to my talk on WhatsApp. All right. I think we have about 10 minutes for questions here. Yeah. All right. Yes, sir.
Hold on, go to Mike.
Was there no security protection in WhatsApp at all?
I can repeat the question. It's fine. So the question was there any security protections in WhatsApp? The answer is yes. There are a lot of security protections in WhatsApp. At that native layer, when I'm talking about PJ-SIP and some of the vulnerabilities found there in the past, PJ-SIP implement something called or PJSIP for WhatsApp implements control flow integrity, so CFI, and that's like a low-level native protection for exploitation. The other one that I would be really interested to see, and I'm not there yet, but the Pixel 8 has implemented the memory tagging extension in ARM, and it would potentially stop a lot of these. Like, if this bug were applicable to Android, I would have really loved to see what it did on a Pixel 8 device that's implementing memory tagging extension. But that's not WhatsApp, that's just the platform itself. Yeah. Thanks for the question.
Oh, sorry.
Yes, sir.
I have a question. I thank you for your talk. I noticed that you had multiple like Python POCs in the middle of the screen. Were these like Frida scripts or?
Yeah, great question. These are Frida scripts. These are Frida scripts, and they're actually hooking very particular offsets within the lib WhatsApp binary. Yeah, thank you for that question. And they are Frida scripts. Yeah, cool.
So my question is about how you approach your research while doing it. We've seen you dumping a lot of stanzas and playing with the filters. Is it mainly how you try to find interesting path, or do you before spend a lot of time in the application and in Guidera to maybe find ideas to trigger, or do you mainly play with it until you find something interesting?
Yeah, great question. So how do I concoct my ideas for potential bugs? Perhaps the one that illustrates that the most is the voice chat bug. So that's me looking at stanzas and maybe looking at like the decompiled code, seeing what strings are in there. And I go, oh, there's like this silence thing. What is that? And I go, okay, well, silence is kind of interesting. What are all these like values I could use? All right, well, this value does something weird. And it sure would be funny if I could inject or make them stream their video back to me with this. So that's kind of what I do is I start with like a feature, and then I start thinking what sort of things would be bad from a privacy perspective or bad from a memory corruption perspective in this space. When you see raw data being injected somewhere, I think that means that you're about to have a deserialization bug on your hand. So definitely think deserialization when you see byte streams in places like this. Yeah, thanks for the question. Okay, yeah, over here. I can repeat it if you want.
Is it like an open format So is it like an open format where you had to reverse the serialization of the stanzas on your own?
So for the question being for that byte stream or the stanzas in general?
The stanzas in general.
So for the stanzas in general, there's actually a function in lib WhatsApp that is like one giant function, and it has like a switch statement. It's like, oh, if your ID is this, it's this stanza, and then it gives you all the like content of what any given stanza should be. So you see this huge function, massive switch statement, and then stanza, 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 stanza. So yes, but no, because it's so easy. Yeah. And if you're interested in that offset, if you come up to me, I can potentially hand that out. So yeah, cool. Okay, I know Travis is up next, and I don't want to keep him. So if there's no more questions, thank you all very much, and have a nice day.